Today I'm going to talk about computational pathology mainly, because I'm working on this area from 2019, I think, until now. So I go through all the stages from the very beginning ResNet until the vision transformer, and now I have a lot of different foundations. So I'm going to introduce several works to link my whole research career about computational pathology. And first of all, I want to introduce a little bit about me and myself. And my background is purely computer science. So my bachelor is about EE. So, but in that time, I already do some programming stuff, coding. And for my master, I'm doing master in Xidian University, also in China. And basically it's from the Department of Artificial Intelligence. But in that time, I'm working on natural images and also some military images. I don't know if you are familiar about that, but it's called hyperspectral images, and with a very high channel but low spatial resolution. And then my PhD is in Department of Computational Science, and which I was focused on the deep learning architecture and also mainly work for medical imaging. And also during my between the master and PhD, I decided to work for a while, and I find I'm not very suitable for working in a big company. I worked in Huawei for 2 years, but in that time it's really good experience because I learned a lot about building large scale software and system, and also familiar with different type of coding like C, Java, and as well as Python. And last thing I want to mention is because most of my work is about computational pathology, so I have a lot of opportunity to gain knowledge from all the collaborators, the pathologists, either from China or from UK here. So it do help me a lot to do the development of computational pathology tools. And still my research interest is about pathology. So from different level of pathology, like from cell, tissue until the slide level. And the working areas is around data set creation, automated diagnosis, prognosis, response prediction, and also some of my side work is about safety and security of computational pathology, absolutely. And just some brief introduction about what I have done or my group. Here I mentioned I don't have my own group. I'm a postdoc in Cambridge, but still I have a group of students who are in China now, but they work with me. So I kind of supervise several master and PhD students. So we do the work together. And at the slide level, it's beginning from my PhD. We start to focus on how to do the slide classification at that time. And this is the first paper about the slide level classification. And then we have some follow-up work. We do at that time, we not really focus on the multi-instance learning, which is the mainstream paradigm these days for slide level analysis. But in that time, we focus on the semi-supervised learning because we ask the pathologists to do some very few annotation, and we try to use that very few annotated point to guide the learning of the whole slide. So it's not very common these days. It's very old stuff. And still, and based on this framework, we try to do some accelerate for the slide level analysis based on uncertainty analysis. And then because everyone is put effort on multi-instance learning, so we have several papers about multi-instance learning. Like this one is hierarchical graph-based multi-instance learning, mainly focused on how to do the PT staging in pathological images. And also we have multi-cell graph transformer for whole slide image analysis, and also some heterogeneity embedding with a prototype-aware graph learning for whole slide image analysis. And also the prototype attention-based machine learning, different kind of multi-instance learning method. And at the end, last year, we have a very brilliant work finally comes out. It's called SMMILe. I will introduce it. This is the main topic I'm gonna introduce today, is how to enable accurate spatial quantification based on multi-instance learning. Because multi-instance learning, you can only know like heat maps, but in this SMMILe framework, we try to have very precise like instance or the region level classification based on only slide level supervision. And also, we have a work is not accepted yet, but it's under review and Nature Communication. It's about a vision language model. I'm not go through this work, unfortunately. Sorry, Philip. But this is basically how we build multi-instance learning framework to connect with larger model to produce like a question answering or possible report generation framework. And some of the side project, we focus on out of distribution about computational pathology because we have a lot of foundation models. It's all training on specific data set. All they said is general, but sometimes you still have some outliers. How we detect those outliers? We have this model, and also most of these days they focus on the slide level classification or patch level classification. But how we do segmentation at the slide level. You can do segmentation at the like the patch level because the limitation of your GPU. So in this work, we also discuss how we expand the segmentation from the patch level to the slide level. And also another work I'm going to introduce today is about foundation model. A lot of foundation model work today, but they mainly work on how much data we can get and how we can align with some molecular or report signals, but they didn't really care about the structure of the foundation model framework. So I'm gonna introduce later. And this is like slide level analysis. And also we have some work around tissue and cell level analysis. Like, first of all, we have some nuclear grading, which is mainly about nuclear segmentation plus nuclear classification, focus on the very specific topic, clear cell carcinoma grading. And also we have this representation learning framework for tissue segmentation. Basically, we want to transform like because the contrast learning or the self-supervised learning is very popular for classification tasks, but not very popular for the pixel level like segmentation. So we expand the contrast learning from the patch or image level to the pixel level. And based on that work, we have this follow-up study, mainly use like, we call it like prompt guided interactive segmentation for pathological images. Basically, the only thing you need to do is do some click on your images, and based on your click, the point that you selected, we do the segmentation. And also we also explore how we can do the domain generalization across different institutes, different tissue organs to have the robust segmentation methods. And this is part of like work focused on the region level classification, because mainly work I introduced before is about slide level classification, but some of the pathology just think actually it's more important to do some subtle or fine grade classification for the specific area. So we have those series works focused on this kind of topics, like like leukemia classification, or we have the pre or early cancer lesion classification, or the anonymous detection, and also some of them focus on the spatial transcriptomics prediction from the spot image. So back to the main topic today. I'm going to talk about two papers. The first paper about SMMILe that we published last year. It's mainly is a work about weakly supervised spatial lesion distribution modeling method. And the other was about the foundation model. And we're gonna start from the first work. And all the work is beginning from the digitalization. So we all know that at the very, very beginning, like 10 or 20 years ago, we don't have this like scanner. And because the scanner technique improved, so we can have a lot of digitalized slides to analysis. This is where we begin. And the workflow are actually different when we have the scanner. So before we have the tissue preparation, we have the glass slide, and they need to send to the lab or send to the pathologist office to do the manual or based on their naked eyes to do the analysis. And then if you have digital pathology, you just need to do the scanning, do the digitalization and the tissue center, and it will be automatically sent to the pathologist or sent to any other computational aids models to do the analysis and then checked by the pathologist too. It's very much more efficiency compared with the traditional workflow. And especially for some of the tasks, like if you based on macroscopy, you only can, like pathologists, they have limited time, so they only can do diagnosis, like the gastric cancer is high differentiate, poor differentiate, or miscellaneous. But it's hard for pathologists to do the quantification, like how many percentage or the proportion of each histotype. So, but actually some of the portion of the subtype is actually important for downstream analysis or downstream treatment. And another example about nuclear counting, like the pathologic only can do the nuclear grading based on several typical region of interest, but with computational pathology, you can really count all the cells and count the number of each cell grades. So basically the changing is from qualitative analysis to the quantitative analysis based on computational tools. And those computational tools can provide clinical evidence, can do the histotype quantification, and even for our biomarker discovery at the end. So back to 2020 is very general solution when people first touch about the computational pathology. But at that time, we don't have foundation model, we don't have very fancy like the multi-instance learning models. So people do annotation for at the slide level, and not slide, at the pixel level, and it takes a lot of time. And then we do the patching, and we assign the label of each patch, and based on the label of each patch, we train our model like in a fully supervised learning way. We do the cancer region detection, subtyping, and even other tasks. And then at the end, we do the aggregation. We either do major voting or any other aggregation method to aggregate the patch level prediction result into the slide level. It's basically like very beginning workflow for computational pathology. But the main issue is, do this kind of detailed annotation take a lot of time about the pathologist? They're already busy now. If you ask them to do this, it will be very annoying. The other thing we need to mention here is slightly different from the pathology images, is different from any other medical imaging or natural images because it's extremely huge. It's most likely like more than several gigabits per slide, and also for the annotation, it's not just focused on one magnification because it's a hierarchical structure. So if pathology want to do an annotation, it will zoom in, zoom out, and several times. So it's definitely not very easy task. It's a very labor task. So we don't want any annotation. So what we can do, so we can extract labels, patient level labels from their report, or we have the pathology report like related to each of the slides. So basically it's easy to get patient level, or we call it slide level labels, any stage, grade, or subtype from their report. So what we want to do is we want to build a model. The input is the slide and also the label that we extract from the report to guide the whole model to modeling the relationship between the slide and the label. So the traditional way is you need annotation, like you need to know which part of the region is positive, which part of the region is negative. But now we have multi-instance learning, which have the conception about the bag, right? So if the bag contains all the negative like patches, we call it negative bags. If a bag contains any positive like instance or positive like regions, we call it a positive bags. So the final optimization goal is not about to classify each of the each of the regions into one category, but we classify each bag into one category. It's a negative bag or a positive bag. So the way to do it is instead of having the region level annotation, we already have the slide level annotation. We still do the tessellation. We have a lot of like thousands of, 10,000s of patches from each slide, and we embed each patch into a vector, or we call it embedding, and then we train a machine learning framework to basically assign an attention score to each of the patch embeddings. Then we aggregate them into a slide level representation, and we classify this slide level representation into one of the category. And based on this attention machinism, we also can get attention visualization from the attention scores. Basically, which part of the region is contribute more to your final prediction, it will highlight it in the final map. So based on our analysis, you can see that as the old ages, if you use ResNet pre-trained on ImageNet, the performance of different machine learning model kind of have some benefit if you have very good machine learning model. But nowadays, if you have Conch or Uni as a foundational feature extractor, you can find that most of model actually is like competitive with each other. It's no such difference. So the thing is because we already have very good accuracy for the slide level analysis. So how we tell people why those models made the decision? How could they provide very accurate spatial quantification as well? And we analyze the quantification results of each model. And some of them is actually only focused on very few regions, as we can see from here. And it made decision only based on several patches. So it can not used for spatial quantification, and even for our clinical pathologists, they can't believe this result because you really focus on very tiny part of the slides. And some of them do give you better quantification or spatial assessment, but still it have a lot of misdetection error. So you can say qualitatively it makes sense. You focus on several regions, several important regions, and you make your decision. But still, this result cannot be used to to tell you how many tumors this patient involved, or the proportion of different subtype regions, right? And some of them give you much better recall as we expected, but it still give you some false negative here, and which still not very trustful. And so basically the quantification, nowadays all the machine learning framework have the false alarm issue and also the misdetection issue. So it only can do very good slide level analysis, but when you really focus on the region level analysis, it's not very perfect. So could we design a model for both accurate slide level classification and also spatial, or we call it instance level quantification, right? It's beginning from what we did at 2020s, but at that time we noticed this stuff. We want to do quantification as well as slide level classification. So we ask our pathologists to do some annotation, they only need to click some point at the tumor region and click some point at non-tumor region. It's very much inefficiency compared with the region level annotation. It's only 10 seconds per slide compared with 5 or 6 minutes. And based on this annotation, we designed a semi-supervised cancer detection framework. The first step, we detect the cancer regions. And then the second step, we use a detected region to do the class, do the subtyping model training. And after that, we can quantify the tumor regions of each slide and also give you a subtype label. And it will show a better performance than if training other very basic models, because it's 2020, so it's no much very famous models at that time. But the problem here is it's like a two-stage training framework. So we're missing the inherent interaction between like tumor detection and subtyping task. And also, if you have some mistake at the first stage, this error will propagate into your next stage. So we decided to design this semi-supervised multi-task learning framework that we published in 2023, but it's actually already done by in 2021. So it takes ages to publish work on journals. So basically, we after the backbone, we have patch level like embeddings. So they all go through two branches. The first branches we got the cancer or normal. The second branches we got the subtype of each patch. And the main design here is the cancer and normal probability that we predicted is guided learning of subtype classifier. If you've been classified into cancer, which means your contribution to your subtyping classifier will be very high. If you classified into normal, based on your probability, we will shrink your contribution to the subtyping classifier, which makes sense because the normal tissue won't attend to the subtyping classifier. So this is basically our design here. Then we test the performance on three data sites, all from TCGA, the renal cell carcinoma, breast cancer, and lung cancer. We show that we achieve the best performance and compare with, because claim and attention-based machine learning is already there and that year. So we also compare performance with them because we have some few like annotations. So basically it's meaningful, so we get better performance at them. And also the reviewers ask us to compare the like quantification ability among the machine learning and also our semi-supervised multi-task learning framework. You can see that compare with claim or MILE, because the annotation that we have, we can much more better quantification performance than claim. Like here you can see it's like 97% AUC compared with 85%. But still annotation are needed. So can we only use, and also this framework, we design like tumor detection and subtyping. So it only can be used for some homogeneous tumors, like a slide only contains one kind of subtype, but cannot be used to have several mixed subtype cases. So the next thing we want to solve is we want to get rid of all annotations. We will embrace the machine learning, and also we want to do some multi-class classification or multi-label classification, which for each case might have several different subtype or histotypes. Right, so we start to rethinking the whole machine learning framework. Basically, machine learning is composed by three components. Like they have a backbone to extract your patch level features. They have an attention network to decide the contribution of each patch. And then they have a classifier to classify each patch or each slide into a specific category. And there are two main like paradigms. And the first one is representation-based attention MILE, which is mainly very like a SOTA method nowadays, and most people follow this paradigm because you aggregate your patch level embedding through your attention network, get the slide level embedding, and then you classify each slide level embedding into a category. And the instance-based attention MILE is not very popular these days. And because normally it gets worse performance than representation-based, we'll introduce later. And so basically you got your patch level embedding for all the patches, and then you classify each patch into a category. You already get your like patch level scores or patch level classification results. And then you use attention network to aggregate all the patch level prediction scores into a slide level scores. It's more like a late stage fusion, and the representation-based MILE is more like a intermediate stage fusion. If you're familiar with multimodal learning stuff, it's the same conception. And so we think about our semi-supervised machine learning framework is actually part of MIL, as we assume, because we have a backbone here. The cancer region detection classifier is actually our attention network, but it's only like positive and negative attention network. And also we have a classifier which we was defined it as a subtyping classifier, but still is mainly the classifier as machine learning. And the main difference between them is our semi-supervised multitask learning framework is actually equals to loss-based attention machine learning, because we multiply the attention score into the losses directly, and the gradients actually are same as the instance-based attention MIL, and the representation-based attention MIL is, we have the theoretical proof here, is actually equivalent to the logic-based attention MIL. Like if you go through a linear classifier, it's just not do the activation function mapping. Before the activation function mapping, it's actually the same as representation-based MIL. So then we try to find the difference between representation-based and instance-based MIL. So representation-based MIL give you better quantification result, but it have a lot of false alarm. And the instance-based MIL give you more accurate detection result, as we assume, like it, but it only can focus on a few positive instances. So they do have advantages, but they all have their disadvantages. So we do some like theoretical proof, and we do some synthetic analysis to find the core reason. And finally, our conclusion is the multi-instance learning, like instance-based multi-instance learning, will give lower attention score to low discriminative and non-discriminative instance, but it will give higher attention score to those with highly discriminative power. So basically, it will classify all the non-discriminative instance into negative like instance, but still it have a lot of misdetection because it will also give lower attention score to low discriminative instance, but it get better result for the like the highly discriminative power cases. So based on these advantages, we developed the SMMILe, and basically we have two main parts. The first part, we have this categorical-wise classification detection branches, which can help us to handle the heterogeneity cases with multiple like subtype within the same slides. And also we have several designs here to help the instance-based MIL to get more accurate spatial quantification results. And first of all is the dropout framework, because the instance MIL only focus on very few high like discriminative instance. So what we think is we just drop those high discriminative instance and force model to focus on rest of the instance, right? It's very like intuitive design. So we have this dropout framework, instance dropout framework. Then we think we want to involve more like different kind of combination of bags, not only related on the 4 bags of each slide. So we have a delocalized instance sampling. Basically, we do the super pixel segmentation to segment each slide into several subgroups, and within each subgroup we do the sampling, right? We sampling one patches from each subgroup and compose a new bag, and based on different kind of new bags we retrain the whole framework to force the model to pay more attention on like within different pseudo bags to get more attention to some of the instance with low discriminative ability. And the final stage is because we force the model to focus on more regions, and but still this is more on like the attention level. So if you want to have a instance quantification, you need a unified classifier to do that. Otherwise, you need to define a threshold, like you don't know like how to define a threshold within each, you know how to design a threshold within each slice. Like if you set it 0.5, it will give you an attention map. But if you give you a 0.3, it may be like recall more regions, but it still have even recall more false alarm, right? So we want to know, like we didn't want to cite like the threshold for each of the slides based on our naked eyes. We want to have a unified threshold for all the slides within our dataset, or within the whole like training domain. So we have this Markov field-based instance refinement framework because we have the attention score from the previous modules. So we can select top maybe 10% of instance. We give a pseudo label, tag it as like the positive instance, and also we can assign the negative labels to the bottom, the instance with lower attention scores as the negative labels. So we have this self-training process to train this instant level classification methods. And also with this Markov field, we can control like the instance within the same subgroup should share the same like scores, or they have the similar scores. So basically like the smooth control. So finally, we evaluate our framework on 1, 2, 3, 4, 8 data sites and across different kind of computational tasks. And it do show, this is a similar picture from the previous one. It do show the like the dark blue is our model SMILe. It do show the comparable performance at the slide level classification. But when we go to the spatial quantification result, or we call it instance level classification result, it shows much better performance than others at the ResNet setting, and because it's foundation model age. So the reviewers asked us to include the conch as a baseline here. So all the model equipped with foundation model have a lot of gain at the spatial quantification, which is amazing. And also we still show like our model have the much better, not compared, like not much as ResNet setting, but it still have a lot of gain from our framework. And this is some ablation study. You can see the huge jump between index 4 and 5 to 6. If you can see from the brown color to the dark blue color, this is mainly gain from the instance refinement module, which you train an instance level classification network based on your attention score. This is several visualization. You can see that our model SMILe is more consistent with ground truth than any other models. And more results, this is some heterogeneous cases, which you not only have a tumor region within each slide, you have like different kind of subtype within each slide. It can show that we can handle this kind of more complex scenario. And it's just more cases here to show how good the spatial quantification we can make. That's all. So summary, we have a high quality host-dynamic classification and spatial quantification with only patient level labels, which called SMILe, and it's already being evaluated across 6 cancer type and some diversity classification tasks, and it has potential in the future to do the like the unknown phenotype identification, like correlated with some genotypes. And we nowadays we already have some results. We implement SMILe into the biomarker prediction, like this EMT biomarker for clear cell renal cell carcinoma, and we extend SMILe from a classification framework into a regression framework. It all shows better results than the SMMILe, and also this HRD prediction, which I mainly work on these days. is related to the ovarian cancer, mainly for the PARP inhibitor treatment. It also shows SMILe regression is better than any other models now. But we haven't really looked at the spatial quantification, because for the biomarker, the most hard thing is how to evaluate the spatial, like the contribution of spatial quantification maps with the real map. So we want to find some spatial, like transcriptomics data to align our prediction results, like spatially, to see if we really get something spatially. Next work I will make it more quicker. It's about CARE. It's our new foundational model for slide level analysis. So back to this very general multi-scenes learning or slide level analysis framework, you mainly have two important parts. The first part is how you do your future extraction of each patch. So before we use ResNet or like any other like model trained on ImageNet, but now we have pathology foundation models at patch level, like Control Uni. So we basically use those models to extract the patch level features. And then the next stage, we normally train a specific multi-instance learning like aggregator for different kind of downstream tasks. And now we all know like Titan or Threads, like different gigapaths, they train their own slide level aggregator based on the patch level embedding model. So they basically stack together. You have patch level foundation model, you have your whole site image level aggregator pre-trained to do some downstream tasks without any like training, or you can do very simple linear regression, or just one layer MLP is enough. So this is the framework of Titan. It uses a huge amount of slides, more than 300,000 slides to train the whole framework, which is insane for us to access that much data. And also this Threads, I don't think it already published, but it's on archive for several months. From the same group, they have 47,000 host images paired with both RNA expression and DNA mutation data to train this framework, and it shows better performance than any other like vision only or vision language framework. And all those framework are just using more slides, more patches, and follow the generic patch aggregation strategy. From patch to slide, this like the same general aggregation strategies. So we think about, is there a smarter way to model spatial topology and multi-scale tissue hierarchy during the foundation model training? So when we look back to the all the model architectures, there is actually a model called HIPT, which use the hierarchical transformers to build the whole aggregation process, from the cellular level aggregation into the patch level, from the patch level into the region level, and finally from the region level to the slide level. But the main issue here is similar as what we do chunking for text, right? If you think about each of the letter is a patch, it's like from patch to slides, it's more like you just chunk your the word or sentence into several letters, and then you aggregate them together. And the other way to do is HIPT with the previous CVPR paper. They use a fixed window to cut the host images into different regions. So you aggregate your, like in text, you aggregate your letters into a fixed length of the chunks here, but you cut the information across different words, right? So the more meaningful way is like if you use the finger space to cut the sentence into several words, it's much more meaningful, because in natural language, we have those finger space, but for histopathology, there is no finger space between different region or between different meaningful segment. So what we do is we design an adaptive region generator upon the fixed window, and during the foundation model training, we try to optimize the combination way of patches to form the region. It's not just a fixed square window. It will optimize the structures by itself. So basically, this is the training framework for foundation model is similar to what Trident use. The difference is we have a adaptive region generator at the medium part. So basically, this is an eyeball training framework. You have teacher, you have student. I won't go to much details, but we have adaptive region generator at the middle part. And what we do this is basically we have the patch level representation, we have a region level, which is initialized by just fixed window. So we calculate the similarity between the patches and only top three regions. Because if you calculate a patch with all the regions, the computational cost will be insane. So we only calculate the neighbors, the patch and also the neighbor regions, and then we choose the top one of them to assign these patches into that region. So basically we have this it's not very optimal design, but it's a current solution. So at the end, we have the adaptive region, we have the adaptive region embedding. So use the same way as SMMILe did. We use aggregation across all the regions into the slide. So from the patches to the adaptive regions, from adaptive regions into the final whole slide image feature. And after this design, we also aligned our slide level features with RNA and protein expression. We use like a single cell GPT as a pre-trained weight to optimize the RNA expression. We use ESM2, which is a protein name embedding encoder, to initialize the protein embeddings. So basically, across this multimodal align framework is to improve the results at the end. So from the data cycle point, the only thing we can access is public available. So we have TCGA, we have GTEx, is normal tissue from all the donors. And we got more than 3,000 slides, and only part of them have paired RNA expression or protein expression. So compare with Titan and the other threads, it's only like a few samples we have. Here is the comparison between all the foundation models from the statistic view. So basically, we only use 1/10 of pre-trained data as Titan use. So this is the result we got. The lighter means better performance. We evaluate across 33 different tasks, and it shows we couldn't say the model we built CARE is better than Titan, but we can say it's definitely a good competitor with Titan, and it's only used 1/10 of data. And this is a small result. It can be shown that Titan is better at morphology classification because it have a lot of data. It's aligned with the report, and also we perform better anti-molecular or survival analysis tasks because we aligned with RNA expressions, which Titan didn't, right? And this is some visualization results shows, and you can see the adaptive region is really not just a bounding box or a fixed window. It do optimize the combination of patches, and it show much more better alignment with the annotation here. And the interesting thing we find is CARE can provide you a region of interest level embeddings. And for some of the tasks, actually is about some very fine grade classification or some mutation prediction. It's get better result if you only use region of interest level embeddings, because we all know that the slide level embedding is kind of like average of your whole slides, but some of the mutation may only happen in a specific area or specific region. So it makes sense, like use only region of interest in embedding to do some of the tasks in the future. And this is the conclusion of CARE, like molecular guided foundation model with adaptive region modeling. And we only use 1/10 of pre-training data and already outperform any like other foundation models. And it shows like strong potential as a disease specialized foundation model because we only need like small amount of data compared with other general foundation models. So this is what we're gonna move for the next stage. We want to specialize foundation model into several specific scenarios. And that's all today. And thanks for my lab in Cambridge and also the lab in China is all contribute to the work that I introduced today. Thank you. Happy to take any questions.